One, thank you for joining me today. Today I will cover a very important concept which is often overlooked when we design practical machine learning systems. So today I will talk about weighted and unweighted accuracy. And this is in reference to machine learning systems. So machine learning systems is, you might be knowing before watching this video, is we have labeled data. So we have data and we have some labels attached to the data, and we use such data for training machine learning systems. So machine learning systems are similar to artificial models for learning. The way we learn, similarly, we learn through our experience. Similarly, the machine learning systems are trained to learn from labeled data. So typically, we divide our data into three portions. The first is the training set. So this data is used for training the neural network machine learning models. For example, the syllabus in a school or college is used to train human engineers to do certain things. Development set is a validation set. This helps us in knowing if we have finished the training process or not. We should stop training process or not. So you can take it like final exams in college. And the testing and evaluation set is the real testing. So it's the testing the machine learning model on new situations, new data. This is like a real world job when a person graduates and join a company. So these data sets should be different and to make sure that learning happens. So for example, let's say we have a neural network system. It's a machine learning system, and this neural network is like an artificial brain that learns to recognize emotions in speech. So for training such a system, there are a lot of approaches. I'm not going to talk about those approaches. However, let's see what such a system does. It takes a sample of speech data, for example, a 5-second audio clip, and it infer the emotions which are contained in the audio, emotions of the speaker. So let's say there could be happy, sad, neutral, anger, or excited emotion state. Typically for training such a system, we use numbers to represent these classes. For example, number 1 for happy, 2 for sad, 3 for neutral, 4 for anger, and 5 for excited. So is you understood? There are two important things for this neural network. One is the speech data, and second is the corresponding label. And these two components are the training sample, speech training sample, and Y is the training label. So for testing the accuracy of this network or any other model, we can do it with two different ways. Usually what we do is we compute the unweighted accuracy. So typically in daily life, when we say accuracy, we mean the unweighted accuracy. So what does it do? So let's say we are testing this neural network and we pass several audio clips of each of 5 seconds with this neural network, and then we get the predictions of the emotions. Okay, so let's say we gave an audio and the emotion predicted happy. So if, and also I know the actual correct label, if my predicted label is same is the actual label of that speech data, I say that it is the correct classification. So unweighted accuracy is that we count. So here we count the number of correct predictions. This is the pound sign. Pound sign represents the number of or count of correct predictions. So how many times I correctly classified the audio, and the denominator here is the total instances. So how many number of audio clips which were passed to the neural network. So let's say I passed 10 clips to the neural network and 8 of those were correctly predicted. In that case, the unweighted accuracy becomes 8 by 10, which is 80%. So if you know that in our daily life, we count accuracy in this way. For example, if someone asks me to guess the weather tomorrow and I guess it is 5 degree, and I can be wrong or right. And if someone counts my predictions and the actual weather for 1 month, they can take the number of times I correctly identified the weather divided by total number of days where I made such predictions, and that becomes unweighted accuracy. However, for a machine, for evaluating a machine, it's very important also to take into consideration the label set. For example, let's say we have a data where the 90% of the audio clip is neutral. And this is also true. So in our daily life, when we speak or talk, we are neutral for majority of the time. We are happy for a fraction of the time, let's say 20%. We are sad for a very small fraction of time, let's say 2%. And we are very seldomly angry or excited. So the label set will be unbalanced. A lot of data will belong to neutral class as compared to happy, sad, or excited class. So for taking into account the unbalance in the label corresponding data set, scientists developed the weighted accuracy. Well, it's a very simple concept. So here we compute class-wise accuracies. For example, we compute how many times we correctly predicted the happiness. Then we compute how many times we correctly predicted the sadness, and so on. And we take the average. So here I make a small mistake, weighted accuracy, just to, and I think you can guess. So the weighted accuracy is the average of these accuracies. I just computed the sum. We should have 1 by 5 times summation 1 to 5 number of correct predictions corresponding to ith class divided by total number of labels for ith class. So this total means we had total number of, let's say I have 100 clips and 20 of them is happy, or 10 of them is happy, and I correctly predicted 5 of the speech samples is happy. So my accuracy corresponding to happiness will be 5 divided by 10, which is 1 by 2. And I will compute the accuracy for each of these classes separately. And this total I in the denominator is the total number of ground truth or actual classes of that data set. So if I have made a lot of data with neutral here, the accuracy of the neutral, the numerator is divided by total number of actual neutral we have. So in this case, in this way, we are trying to weight the correct number of samples with the actual number of samples for each of these classes. So in this way, this represents the accuracy in a more sophisticated and more accurate, or in a more appropriate manner. Let's say we have a data with where the 99% of the data is belonging to neutral class, and I designed a machine learning model, and the prediction accuracy of the machine learning model is 99%. What could be happening? It could be happening that the neural network is predicting neutral every time, irrespective of what kind of data you gave. It is always predicting the 99% accuracy because of neutral. And we might think that this model is very good and we can deploy it in a product. However, this model is terribly incorrect because it is always pretty neutral. However, we will not be able to know it from unweighted accuracy. We have to look at weighted accuracy for guessing such cases. So in that case, the weighted accuracy corresponding to all the 5 classes will be the average of accuracies for each of these classes. And since the neural network is predicting neutral 99% of the time, we have 99% corresponding to neutral and 0% corresponding to each of the 5 classes, other 4 classes. So the average will become 1 by 5 into 0 plus 0 plus 0 plus 0, 4 times 0 for other classes, plus 99% for the neutral. And now 99 divided by 5 is approximately 19 point something, approximately 20%. So this show us that there is deliberately something wrong with the doesn't classify. So for extremely unbalanced data sets, the weighted accuracy makes more sense. And as the unbalanced data set increases, it becomes more crucial and important to account the weighted accuracy. Okay, and we will try to understand it with the help of a numerical example. So now let me, well, I think most people know the meaning, but when I say balanced data set, what does it mean? So it means that we have seen, I will use count for the count or number operator. So same number of instances from each class. What does it mean? It means I have 20 audio clips for happy, 20 audio clips for sadness, 20 audio clips for neutral, 20 audio clips for anger, and 20 for excited. So here, number of audio clips for each of the classes is same. So this is called a balanced data set. So data set is balanced with respect to the labels of the data. So if you see, the balance is more about labels than the speech. An unbalanced data set could be when we have different number of instances. For example, we can have 10 for happiness, 10 for sad, 30 for neutral, 20 for anger, and 10 for excited. And also practically when we go and collect data from users, or we try to collect data by some control studies we perform, it's a very difficult to get a balanced set. Typically we get more neutral, always we get more neutral than any other emotions in the emotional recognition. And that is why emotional recognition using a computer is very challenging, and that is why we are still struggling to make a very practical humanoid robots. So here, let's look at the right side where I have a true output. So this is the actual level of the data, we know it. So this is like 1, 5, 3, 2, 4. Here 1 is happy, 5 represents excited, 3 represents neutral, 2 represents sadness, and 4 represents anger. And prediction, typically we represent it with y hat. So this is coming from the neural network. So we pass data from neural, after trying the neural network, we test it and then we pass different data and predict. So if it was 1 and it predicted 1, we say this is correct classification. And if it says 3 instead of 5, it becomes error, and so on. So corresponding to this, we make a confusion matrix here, the left side. People call it confusion matrix, and I will go through it again next page. But let's see this figure once again. So here we have the top heading, happy, sad, neutral, and so on. So this represents the actual class, and the y-axis, which is happy, sad, neutral, excited, represents the predicted class. So what does it mean? It means that if we see the first column, we are seeing how many times there was a happy and we predicted happy. So there was 5 times I predicted happy and I had happy. Let's see the second one, first column, second row, I had the happy was never classified as sad, so it is 0. Third row, the happy was classified as neutral 1 time, so we put 1. And in the first column, fourth row, we see that the happiness was classified, if happiness was classified as anger, we put 1. And if the happiness was classified as excited, we put 3, which is the last row, first column. So in this way, each column is representing what was the distribution of each of the predictions. So the sum of the first column is the total number of happiness data we had, and then for each row it is showing that how many data was predicted to be in that class, and similarly for other. So in this way, if happy was predicted as happy, that is 5, it means we make 5 correct prediction, and the rest was incorrect. Similarly, for the second column, when we have sad, we had 6 sad speech data with sad label, and we see that we always predict sad as sad, so 6 is the correct, and we have never predicted sad as happiness, so it's all 0. So likewise, we see all the numbers on the diagonal of this square matrix represents the number of samples correctly classified with the neural network. So classification and prediction is same I'm using, but classification is a better word. So this is number of things, and also the sum of all the numbers in each column represents total number of data from that class. So here once again we should remember the horizontal axis, the x-axis is the actual class, and the y-axis represents the predicted class. So now I have recreated the same confusion matrix here just for clarity. So and people call it confusion matrix, very common term, because it helps in understanding the output of the system. So here we understand that some of the happy samples are misclassified as neutral, anger, or excited, and we see that the happiness and excited are being confused with each other. So likewise, so let's see these numbers once again, and let's try to compute the weighted and unweighted accuracies. So when we see we want to compute the unweighted accuracy, it means we will sum the correct classification for all the correct classification, and then we will divide it with the total number of samples we have. So we saw that the total number of correct classification is on the diagonal. So we add all the diagonal terms. So 5 plus 6 plus 7 plus 4 plus 6, and we add it all here. I have circled the numbers to show that they are from the diagonal. And now we will divide it with the total number of samples. So we see total number of samples means sum of all the numbers. However, each column represents total number of samples from that class. So sum of first column is number of happy samples, actual happy samples we have. And the sum of second column represents the number of sad samples we have, actual number of sad, and so on. So we add all the columns together to get the count for each of the classes, and then we add all these numbers together. So basically sum of all the numbers in this table. So 5 plus 1 plus 1 plus 3, so 7 plus 3 is 10. So we put here 10 plus 6 for the second column. Third is 1, 2, 7 plus 3 plus, that is 13. So we put 13 here. We had 1 plus 1 plus 4 plus 1. So it's 3 plus 4, which is 7. And then we have 3, 2, 5, 1, 6 plus 2, 8, 6, 14. We add here. And so it becomes 28 by 50, which is 56%. And now for the weighted accuracy, we have to weight the correct classification for each class. So it becomes 5 by 10 for happiness. So 5 was the correct classified happiness, and total happy was sum of first column, 5 plus 1 plus 1 plus 3. So it becomes 5 by 10. Then again, in the second column, we had 6 times the sad was classified as sad, and then we see that total number of sad is the sum of second column, which is also 6. This is 6 by 6, which is 100% for that class. And then again, the for neutral becomes 7 divided by the sum. So 7 divided by 13 is sum, and so on for the anger, 4 divided by the sum of the fourth row, and the 6 divided by sum of fifth row for the excited one. So this is the sum of the class-wise accuracies. And now we have to take the average. So there are 5 classes. We put 1 divided by 5, and it is 60.77%. So now we see that if it's unbalanced, so typically in machine learning research or practice, we have to compare two systems to know which system was good for us and which systems was not good. So if we are comparing on the basis of unweighted accuracy, we can be mistaken. For example, the example which I told earlier, the 99% case, that time we might think the system is perfect, but it is not. And in this case, 60% is far better than 56%. So if we compare two systems in terms of unweighted accuracy, and one of the systems, for example, here the second is a very high number of counts for that system, and it's like very large as compared to all other classes, the unweighted accuracy will be very high, and that can mislead. However, here we see that when we weight the classes, the accuracy is weighted with respect to number of labels for each class, and that helps us in getting a more reasonable number. So as a conclusion, we can remember that for unbalanced classes, we have to choose the weighted accuracy. So this is one part of the story, how to compare two systems. Also, the unweighted classes are difficult to handle. It's hard to train a neural network system on unbalanced class and get good accuracy. So sometimes maybe you might be interested in finding a strategy for making the dataset more balanced. How to make the dataset balanced in terms of number of samples for each label. So one way is that you merge some classes. You can merge smaller or weaker classes. So for example, if you see that there are very few examples for excited and angry, both have very few. So we can add the number of classes from the excited and angry, and by doing that, we will get a slightly larger class, which can be a good representative. However, just adding the classes or merging the classes on the basis of number of labels is not a great idea. For example, if we have very few sad samples, very few neutral samples, we cannot add them together because they are more like a reverse emotion. So it also makes sense to reduce the label space. For example, just consider three cases: happy, sad, or neutral. Or some people call it positive, negative, or neutral. So three classes. Let's say there is a audio clip. We just put three samples, either positive emotion, negative emotions, or neutral emotions. And in that way, we have broader categories, and also the data will become more balanced because the things are being added up semantically, which is a better approach. And I know that reducing the positive, negative, and central and neutral space is a good strategy, and a lot of times we get higher higher performance, more robust performance for practical systems. And let's say you divide your data just into three categories. Happy represents the positive sentiment, sadness is the negative, and the neutral is the 70. You can always drop some of the data from larger set. For example, here, if we have 15 audio clips for happy, 20 for sad, and 70 for neutral, we can just go ahead and choose 15 for each of the happy, sad, and neutral in the training set. And in this approach, the size of data is reduced, but data is balanced. And a lot of times, if this number is big enough, for example, it also depends on the type of model you are choosing to train. If this number is significantly is big enough to be able to train the network, this is fine to drop the data from the larger class, which is very massive. So these are three practical tips which helps. And a lot of times, any of the three approaches can help you in making the data set balance. It depends both on the domain. For example, you could be doing emotion recognition. You could be doing deception detection, for example, to know if what the speech is deceptive or not. Or you could be doing a speaker verification or speaker identification. You would like to know what was spoken. So in that case, you are doing speech recognition. So depending on the task, any of these strategies can help you, and it also depends on the type of models you are using. For example, you can use deep neural network or a support vector machine or a hybrid GMM HMM system and so on. So these are just general concepts, and I hope this video helped you understanding the difference in the definitions and also to see why it makes sense to consider weighted accuracy over the unweighted accuracy for unbalanced classes. One more comment I would like to give before we close the video, that if the number of samples is exactly the same for each of the classes, let's say each class has T number of samples, then the weighted and unweighted accuracy becomes the same. How? You see the numerator term is same in both of them. If they have the T number of samples for each classes, it will be 5 divided by T, 6 divided by T, 7 divided by T, 4 divided by T, 6 divided by T, and it will become same is sum of all the numerator divided by T, and 1 by 5 we have outside, so 5 times T is also the sum of T 5 times, T plus T plus T plus T 5 times. So the denominator and numerator becomes the exact same in both of the expressions. So unweighted accuracy and weighted accuracy become same for the unbalanced for the balanced data set. For unbalanced, it makes sense, and larger the imbalance, the better is the distinction between these two accuracies. Otherwise, they will be very close. As you see here, the difference is just 4%. But in the case I told you that 99% data is neutral, in that case, the unweighted accuracy was 99%, and weighted accuracy was around 19 point something, 20%. So this is what you need to understand, that when it makes more sense to choose any one of them. So that was it for this video. Thank you, and please leave any feedback for me or a topic which you might want me to cover in the future videos. Thank you. Bye.